All right, well, hey everybody. I just wanted to give an overview of the midterm and what is on it, what isn't on it, things like that. Uh, Basically, the second half of Lecture 19, I already kind of recorded the first half of Lecture 19, so hopefully you watch that. We are going to complete midterm 2 through WebAssign, and so on this Wednesday, April 1st at 9 a.m., I will make the WebAssign exam open. It'll be open from 9 a.m. to 9 p.m. And there's 8 questions total. None of them are multiple choice, sorry. But I'll talk about other things that's a little bit more forgiving than a normal exam in a second. But there's 8 questions total, and some of the questions have multiple parts. So, for example, the last 2 questions have multiple parts. They're basically adapted from the open response in the sort of original midterm 2 that I had. And of those 2 questions that have multiple parts, one is 2D momentum conservation, and the other one has to do with angular momentum conservation. And so those are a lot of the points on the tests are going to be from those 2 problems. These ones there's other questions are just maybe like 1 part or 2 parts, something like that. Each question has a different randomized set of parameters so that no 2 people have the same exam, basically. And what I've done is that, on a normal midterm, you would only have 1 chance to get things right, so to speak. On the homeworks, you would get 10 chances to get things right, and so I feel like giving you 4 chances to get each question right seems reasonable to me. So if you put something in and you screw up the units, you've got 3 more chances to just kind of sort that out. On the homework, the tolerance is plus or minus 2%. So if you use 3.14 instead of 3.141, something like that, this is pretty tight, and I've seen a number of cases in which people that are on the right track, the first 2 or 3 parts of the question are fine, and then the last part is wrong because those errors early propagate to small errors early can propagate to larger errors later. So what I've done is I've configured the exam to have a larger than plus or minus 2% tolerance. I don't want to say exactly what the tolerance is on the exam, but it's more than this, which I hope is helpful. The exam will be open book, open notes, so you can look at all my lectures, all the worksheets. You can use Desmos, you can use graphing calculator, you can even use Google to convert units. Honestly, I think that's going to be pretty helpful to you. So I don't be afraid to use Google to convert units. That's totally fine with me. You can check out the book. You can also look at, say, the OpenStax University Physics textbook, any physics textbook, anything. Open internet, really. Use whatever you feel like you need to use to complete the exam. Now, one thing you are not open to do is you may not communicate with other students regarding the exam during the exam. That's crossing a line. If you want to communicate with other students about Minecraft during the exam, that's fine. But please do not talk about the exam. If you have any questions on the exam, you can email me. I'm pretty good about answering emails. It's on my phone. It's on my laptop. Or you can open up a Zoom session with me. I will try to stay logged into Zoom as much of Wednesday as I possibly can. And I'm happy to answer questions. There's probably are things on the exam that are misconfigured. I've never, this is the first time I've done it in WebAssign. There's probably something on there that's not quite right. So I would not be surprised if you find something along those lines. If you do communicate with other students, I will have to treat that as a violation of academic integrity and file whatever paperwork I need to fill to treat it as academic misconduct, which is a bad thing. I don't want to go into exactly how bad or what the consequences are, but I have to take these things seriously. So please don't talk to other students about the exam during the exam. In terms of what is going to be on the exam in terms of the content. This table is on the equation sheet. The equation sheet's currently on Carmen if you want to check it out. But this table is on there. This table is on there. So I'll give you all these equations. You don't need to memorize these or anything like that. Various other equations you can see with the equation sheet that's there. So again, I'm not going to actually derive any of these formulae. I mean, I derived it for you on one of the lectures, but I did it so you could see where it comes from, not necessarily so I could force you to derive these things on midterms. I'll also include the equation sheet for midterm 1, so that'll be linked to the exam, which you could already look at the equation sheet for midterm 1 because it's open book and open notes, but that's also going to be available to you. Just as a bit of review, so this is the slide that kind of goes over all the angular speed, angular momentum, stuff like that. It's actually from midterm 1, but I think it's good to go over it just to get used to it. The angular speed is omega, and that is the change in the angle of the change in time. Omega, typically we have the angle in radians instead of degrees, which means that this unit is radians per second. So now we're going to relate this to the frequency and the period and things like that. So the frequency is the number of cycles per second. So not radians per second, but the number of cycles per second. And so how many radians is there on one cycle or one circle? Listening. There's 2 pi radians in one circle, and so that means that if you take the angular speed and divide by 2 pi, that'll give you the number of cycles, and so the frequency is omega over 2 pi, like that. So there you go. So cycles per second. By the way, cycles per second, another word for that is Hertz. That's named after a German physicist. Now the period is the number of seconds per cycle. So not the number of cycles in 1 second, but how many seconds does one cycle take. And so, as you can imagine, this is the inverse of the frequency. So 1 over the cycles per second gives you the seconds per cycle. And then, because we know how the frequency relates to the angular speed, we can sub this into here. All right, frequency is omega over 2 pi. That means that the period is 2 pi over omega. So there you go. So that's the period. The next part is maybe the acceleration. I can't remember. Velocity. Sorry. I wrote these slides. I always forget what the next part is. The velocity is, for circular motion, is the distance over time. Well, the distance is the circumference, so it's 2 pi r. And then the time to make one circle is the period, and so it's 2 pi r over the period. Velocity, of course, is units of meters per second. And then, so the circumference is 2 pi r, that's the period. And the units there, meters on the top, seconds on the bottom. All right, so that's the velocity. And then the last part is the acceleration. So the acceleration is v squared over r. I had a whole lecture on why it makes sense that it's v squared over r. This is the acceleration at any point in making a circle. But what's interesting is that we know how the velocity relates to the radius and the period. We know this thing, I should have said this earlier, is that 2 pi r over the period, well, 2 pi over the period, if you stare at this thing long enough, 2 pi over the period gives you omega, and so the velocity is r omega. And so we can stick that into here for the acceleration, so r omega squared. The r squared on the top cancels with the r on the bottom, so we get r omega squared. And there could be some problems in which this version is the easiest way to think about it. Anyway, so this is all review for midterm 1, but I think it's useful for midterm 2. We introduced springs after midterm 1. It was a while ago. There's a lot of stuff that was from a while ago that feels like it was on midterm 1, but actually wasn't. So we introduced springs. There's a restoring force. We talked about there's the natural length of the spring. things like that. We also talked about the energy that can be stored in a spring. Remember, the energy is the force times the distance. And so specifically it's the average force. So if there's some initial force and some final force, it's the average of those two things. For a spring, initially it doesn't take hardly any force at all to get it to sort of compress just a little tiny bit. But eventually when it becomes compressed, it takes a lot of force, and so that's the K delta X there. And so that's the average force. And this times the distance again gives you this delta X squared. And so that's how much energy you can store in a spring, or the work that it takes to compress a spring, one of the two. Yep. And it goes as the square, interestingly. Sometimes you'll see this written like this, which is fine. This is the potential energy stored in the spring. Thus far, there's only really two kinds of potential energy that we've talked about. There's gravitational potential energy, and then there's spring potential energy. All right. There's a nice worksheet from lecture 13 on spring potential energy making Gonzo fly across the room. I really like this worksheet, in which we use energy conservation to find the final speed of the object when it hits the ground. And then we did it sort of like in a midterm 1 type of way, and showed that you get the same answer. It's just energy conservation is a lot faster of a calculation. Basically, all the worksheets are good. I mean, I designed the worksheets and I did design the exam, so if you want to try to get into my mind about what's on the exam, looking at the worksheets is one of your best bets. Collision problems, so there's definitely questions on collisions on the midterm, so be prepared for that. Power is the energy per unit time, and so some of the questions involve power. Like I said, one of the big sort of multi-part questions has to do with collisions. And remember that there's 3 different types of collisions. There's elastic collisions, in which the initial kinetic energies, the total initial kinetic energies, add up to the total final kinetic energies. There's inelastic collisions, in which they do not. The total initial kinetic energies are more than the final kinetic energies, but they don't stick to each other in inelastic collisions. With perfectly inelastic collisions, similar to inelastic, the initial total kinetic energies are more than the final total kinetic energies if you add them all up, and they stick together, which means that the final velocities are all the same. Now, for the purposes of the exam, I'm probably only going to give you elastic or perfectly inelastic. With inelastic, things get a little bit tricky because there's, this makes the math rather nice for the perfectly inelastic. And so this one you have to add in, you have to think about exactly how much energy you've lost, things like, I don't know. These questions tend to be much more complicated than either these ones or these ones. Or for example, if I had a multiple choice question saying like, what type of collision is this? I would probably only give you the options of elastic and perfectly inelastic, because in a certain sense, every collision is inelastic, because if you can hear the bounce, then some amount of energy, that kinetic energy, is being lost to sound. And so if I was going to ask a multiple choice question, I would say something like, most approximately, is this collision elastic, or is it closer to perfectly inelastic? If that makes sense. And remember that I'm telling you explicitly that one of the questions is 2-dimensional. So it's not just in 1 dimension, but we had a group work for lecture 15 that was the 2-dimensional problem. On some level, the programming lab, the reason I like the programming lab, the momentum conservation programming lab, is that it is an example of perfectly inelastic in 2 dimensions, because you have that ball of goo that the ship flies into from whatever direction, and then it drifts whichever way it goes. So that's a two-dimensional, perfectly inelastic. A two-dimensional elastic is this group work from lecture 15. There's definitely some torque and balance problems, and I converted the multiple choice to numerical response, but there's still definitely going to be balance problems, angular momentum conservation. So there is so for a whole year I actually used this OpenStax University Physics textbook, which is free. It's not as good as the textbook you guys are paying for, but it has a lot of good examples in it, so I encourage you to check it out. Yeah, I encourage you to check that out. What might not be as useful to you as the OpenStax would be University of Illinois practice exams. So my alma mater is the University of Illinois, and if you go digging on their websites, you can find their practice exams for this course. I think they have a little bit different emphasis than I do, so again, I would encourage you to look at this. Another nice thing about OpenStax is that they have the university physics, which is the calculus-based physics, which is what you guys are doing. They also have the college physics, which is algebra-based, and sometimes if you're feeling sort of like whoosh over your head with this course, you can go back and look at the college physics textbook to try to figure out how are they explaining it. And sometimes when I'm teaching the course, and I'm trying to figure out like how can I distill this down to the simplest I can make it, sometimes I will look at the college physics textbook for some perspective as I try to teach it at the level I need to teach it. So OpenStax is a really nice resource that I'm grateful that we have. So I think that's about it. But send me an email if you have any questions. And as I said, I'm going to be logged into Zoom and checking email pretty much all day on Wednesday for the exam. So let me know if you have any questions I can answer. So thanks.